Okay, so in the last class we discussed some important facts regarding surf tension, the tension in a string. Right. So today we will be discussing more questions on tension, and then mostly on tension today. So if the time permits, we can start the friction as well. Okay. First of all, I want to make sure is my audio is clear. I mean, do you find anything like lagging? Please let me know through the chat box, or you can unmute and talk. Okay, thank you, Hirosh. Right. So you can right now start writing. So it's yeah. You can start with let us consider. Let us consider. Let us consider a string. A string. A string. A string of density rho. Density rho and cross section. Cross section. Cross-sectional area, so cross-sectional area, capital A is hanged vertically by a rigid support. By a rigid support. Let us consider a string of density rho and cross-sectional area capital A is hanged vertically by a rigid support. So let me consider this. So there's a rigid support, and then string is hanged vertically. So this is the string. Okay, and the density is rho and cross-sectional area A. You can draw this. Also, let us consider the length of the string as capital L. So length capital L. Okay. Mention capital L is the length of the string. Okay. Try to write down an equation for the mass of the string in terms of A, rho, and L. Try to write down an equation for the mass of the string in terms of capital A, rho, and capital L. I'll give you a minute. Okay, and those who are from new batch, okay, you can take a separate book for today's class, right? Uh, because this is we are doing for mechanics, and for unit 1 you have to have another book. Okay. Okay, so you have to write the mass in terms of A, L, and rho. So please try to write an equation for mass in terms of A, L, and rho. If you're done, you can send me your answer through chat box, or you can even capture your answer as a picture and send it to the Knowledge Institute. Try to write an equation for the mass in terms of A, rho, and L. Okay, Hirosh, did you write an equation? Okay, very good. So we know the mass is, we can write as mass volume times density. Let's say the mass is capital M. So we can write volume times density, right? So the volume we can write, so a string is like a cylindrical shape. So we can write here cross-sectional area A and length is L. So cross-sectional area into L, AL, this gives the volume. Okay, so this is the volume into density, we write rho. So therefore, mass is equals to AL rho. Okay, so this is a normal question. So the mass of the string is given by AL rho. Okay. Okay, so the next thing, now I'll ask you a question regarding this. So question number 1, let's say, what is the tension? So you had to write this. What is the tension? What is the tension? Please write down. What is the tension? At the bottom end of the string. What is the tension at the bottom end of the string? Okay. So if you consider this string, now, for example, if there's string, let's say if I have rubber band, okay, if I just hold it, if I just placed on my hand, there won't be a tension. But if I stretch it, there will be a tension, right? Or maybe you can consider a spring. If I just spring, if I placed on my hand, there won't be a tension force. But if I push from both ends, if I pull from both ends, then there will be a tension. Or I can push both sides, like compress. Then then in that case, there will be a compressive force, right? Compression, right? So in order to have a tension, there should be a force, right? But if you consider this bottom end, So at the bottom end, it's free. So therefore, at this point, tension will be zero. Tension will be zero. But if you consider somewhere here, like this point, let's say, at this point, so you can see the mass below that point, the mass of the string below that point will push that down, right? So therefore, there will be a tension. Okay, so now I'll explain this again. At the free end, at this end, there will be no tension because it don't carry any weight. But here, if we consider at this point, it has to carry the weight of this down part. So here, therefore, there will be tension. Now, for example, let's say T1, that could be something around, let's say 1 Newton. Or let's say this mass is like zero point 0.1 kilogram, then it will be 1 Newton. But if you go a little bit higher, somewhere here the tension T2, if I take T2 is greater than T1 because now this part of the string has to carry this entire mass. So therefore, here the tension is higher than here. So this one could be something around like, for example, say 2 Newton. And if you go higher and higher, the tension in the string will increases because each point, when you go higher, each point, the mass that it has to carry will increase. Likewise, then where the tension will be maximum. So the maximum tension will be here at this point. So at this point, the tension will be maximum because it has to carry the entire weight or entire mass of the string, right? Therefore, the tension is minimum at the bottom end and the maximum at the far end. Okay, did you all understand? Please say yes or no. Okay. So what is the tension at the bottom end of the string? So it is zero. So you can write zero. The tension at the bottom end of the string is zero because it doesn't have to carry anything. So therefore it will be zero. So the next question number 2. At which point of the string tension is maximum? At which point of the string at which point of the string tension is maximum? Okay, if you understood, please text the answer, drop the answer in the chat box. At which point of the string tension is maximum? Okay, I got an correct answer. I need a response from everyone. And please drop a message to the Knowledge Institute, not to Rimaz, okay? Yeah. So I'm getting the correct answers at the top end of the string, right? So at the top of the string or the top end of the string. So because here, if you consider this point, that point of the string has to carry the entire weight of the string. So therefore, the tension will be maximum at the top end. So you can write top end of the string. Okay. Okay. And let us try to derive a expression how the tension varies along with the distance. Okay. Now for that, I'm going to consider a part of the string, let's say from a height x from the bottom. So I consider a length of x. Okay. I consider only this part of the string. So this is an enlarged picture. And the length is x. Cross-sectional area is capital A and density rho. Okay. So if I consider this part of the string, okay, so here I can mark okay, the cross-sectional area is, we know it, that is, okay, that's a cross-sectional area. So here the bottom end, the tension is 0. So the tension at the bottom end is 0. Say T1 equals 0. And here the tension, let us take as capital T or Tx, the tension at distance x. So this height is x. Okay. And if we consider this, the okay, so if we consider this part of the string, its weight. Now this has a mass, means in fact it has a weight. So that weight acts from the center of gravity of this part. So the center of gravity of this part of the string. So consider only this part. Its center of gravity will be at the middle of. We had to consider that mass is uniform. The density is uniform. The mass is uniformly distributed. That means you can say density is uniform, right? So if it's uniform, if the string has uniform density, then the mass or the weight of the string acts from the midpoint. You will study thoroughly about the center of gravities in the center of gravity lesson. Okay, so it will be the midpoint. So from here it vertically downward. Yeah, the weight acts vertically downward. And let us consider the mass of this part is simple m. Therefore, the weight is mg, right? So W weight equals mass times gravitational acceleration. Therefore, W equals mg. Okay, right. So then if I consider this string, now we can see it's in equilibrium, balanced. It's not accelerating, it is at rest. So according to Newton's first law, uh, if an object is moving at constant velocity or if it is at rest, that means there is no any unbalanced force. Because what is Newton's first law? Let us recall, unless an unbalanced force is applied, the object is at rest, remains at rest, and object in motion remains at constant velocity. So that means if object is moving at constant velocity means it has no any unbalanced force acting on it. Or if an object is at rest means it has no any unbalanced force acting on it. It may experience some forces, but it will balanced. Now, for example, if I consider this part, now this is at rest, that means it is in equilibrium. Therefore, according to Newton's first law, the forces has to be balanced. Okay. So now if I consider the vertical forces acting on this part of the string, so we can write, so considering the vertical forces, or we can simply write vertical equilibrium, considering the vertical equilibrium, considering the vertical equilibrium. Okay. So what are the forces acting on in vertical direction? So this Tx is there, Tx, and then downwards mg is there. So it is minus mg because I'm considering this equation vertically upward direction. So if it's vectors, you have to consider a particular direction. Right? When we are writing a vector equation, you have to consider a particular equation now. For example, in equations of motions, right? So there also we have to consider particular direction. So these are vectors, force vectors. So therefore, we have to consider particular direction. So tension here vertically upward Tx minus weight vertically downward mg, and then T1 is also downward mg. So this is the total force acting on it. So according to Newton's first law, this has to be zero because object is at rest. That means the force has to be balanced. So therefore, T1 is anyway zero, right? So therefore, we can write Tx is equals to mg. Okay, so we can write this mass m in terms of x because mass in equals volume into density. So volume is a times x in here. The mass of this part of the string is cross-sectional area into the length x will give you the volume into density. So therefore m equals a x rho. Therefore we can write dx as, so I can substitute m a x rho g. So here a is constant, cross-sectional area is constant, density of the string is constant, gravitation acceleration is a constant. So therefore Tx is equals to a rho g. A constant is a constant times x. So variation is, you can see y equals mx. So it's a straight line. Right now you can see when x equals 0, Tx is 0. So obvious, right? When x equals 0, that means at the bottom end, the tension is 0, right? And the tension is maximum when x is maximum. The maximum x value is capital L because we can see that x varies from less than or equal to capital L greater than or equal to 0, right? If there is anything you don't understand, please let me know. So I'll explain more again. Okay. Right. I hope so far everything is clear. Okay, sure. So here we can consider only this part of the string. So that one I have taken enlarged picture here. So at this point, at the distance x, let's consider the tension is Tx. So Tx is a variable, it varies with the distance x, right? So here if you consider this part, I mean this part of the string, here the tension is Tx. So I have marked here, and then at the bottom end tension is 0, okay? And its weight acts from its center of gravity of this part. So it will be center of gravity will be midpoint of this string, okay? So that now we can consider the vertical equilibrium because this string is balanced. It's not moving, it's not accelerating, it is at rest. So that means it has to be balanced, right? Therefore, according to Newton's first law, total force acting on it should be 0, right? So if object is at rest, that means no any unbalanced force is acting on it. So all the force must be balanced. So T1 is already 0. T1 is 0 here. So therefore, Tx equals to mg. And m we can write volume times density. The mass of this part is volume times density. So volume is cross-sectional area into length. So length is x, right? The length of this part is x. So therefore, Ax is the volume into density Ax rho. Right. So now I can take this m and substitute here for the Ax rho. For m, I can substitute. So Ax rho g, A is constant. So it has a uniform cross-sectional area. So therefore, A is constant. Density of the string is constant, and gravitation acceleration is constant. So therefore, this entire term is a constant. So therefore, we can see the tension varies only with the distance. Right? So tension varies with the distance. So this relation is like straight line, y equals mx. Okay, is that clear, everyone? Okay. So you can write down, after drawing this picture, you can draw down this. Okay, you can draw this down, and then we can consider the vertical equilibrium. So it's equilibrium, that means balance means no any external forces acting in that direction. So I'm considering vertically upward direction. In upward, we have only Tx. The weight is acting downward, so I'm considering upward, but weight is downward. So it is opposite to the direction that we are considering, so we have to put minus. So when a certain vector is opposite to the direction that we are considering, that vector has to be minus. So here T1 also downward, it's minus. So T1 is anyway 0, therefore Tx equals, if you take this minus mg to the other side, it becomes plus mg. Tx equals mg. And then you can write an equation for mass in terms of Ax and rho. So therefore, the mass of this part will be Ax rho. So you can substitute for mass in this equation. Therefore, Tx equals A rho g times x. Okay. So the variation is y equals mx. So if you draw a graph against x versus Tx versus x. So here Tx and this is x. If you draw this graph, it has to be a straight line passing through the origin because the variation is y equals mx. So this equation you have already studied in your O levels, right? Y equals mx is a straight line passing through the origin. So the graph is a straight line passing through the origin. And if you find the gradient of this graph, what is the gradient of this graph? So the gradient of this graph is equals to, let's say gradient is m naught, gradient. If I take gradient is equals to m naught. So m naught is equals to, you can see here a rho g. It has to be a rho g. Okay. So please note down this. Okay, I had to write down this. And then after this, and then you can get this relationship Tx equals a rho g times x. And then therefore we can plot the graph Tx versus x. So it has to be a straight line and the gradient of this will give the cross-section times density times gravitation acceleration. Okay, so from this we can deduce the maximum tension, the tension at the top. We know at the top the tension is maximum. So we can formalize, we can see Tx equals to A rho G times X. So the maximum, when X is maximum, Tx will be maximum. Then X maximum X value is capital L, right? Because L is, you can see, is less than or equal to capital L and greater than or equal to 0, right? So therefore, when X equals to L, Tx will be maximum. So T max, we can say maximum tension is A rho G times L. Okay, so you can note down that thing as well. Let me know if you have finished writing this. Hirosh Lele brother. Okay. Those who are still writing, you can take a screenshot. 3, 2, 1. Okay. I hope you have got the screenshots. Okay. Let's clear this. Okay. And now suppose if you consider a light string. A light string. A light string means the mass is negligible, weight is negligible. So light string is negligible weight. That means no weight, negligible weight. If the string is light, okay, so string is light, the tension in the string will be same everywhere. Okay. Now here, let's say we hang a mass capital M, simple M, let's say mass M. So the string has no mass. This string has no mass, negligible weight or no mass, right? Because mass is very small, negligibly small. So it has, this string has no mass, okay? So here, but we hang the mass M by this string. So we know this mass is experience gravitational attraction. So it has a weight in G. Now, for example, now I feel a force in my hand because the gravity is pulling this, but my hand is holding by friction. I have a weight, right? 1 kilogram weight. Then I feel a large mass. I feel I want to apply large force. If I can hold 2 kilogram mass, I want to apply a larger force to hold this. If it's 10 kilogram, so I want to apply more force to hold that, right? Because the gravity is pulling, the gravitational force is there, so that gravity is pulling the mass downward. So in order to keep it in equilibrium, in balance, I have to apply the force that at least equals to the mass weight of that object. Now if I want to hold this, I want to apply the same force. So if it's now, you can see this is balanced, it's not falling because the weight is acting downward and my friction from my fingers acting vertically upward. So exact same value, so that this is balanced. Okay, but if I drop it, so no longer the friction will be there to withstand this gravitational force, so that what happens, this will accelerate. There will be unbalanced force mg downward, so it will accelerate vertically downward. Okay, right. So now what happens now here, if we have the mass mg vertically downward, so due to this mass, it is due to gravity, it pulls this mass, but this mass is carried by the string. So this string will have a tension at this point. So here tension and this tension. We'll mark this tension as capital T. Okay. So here, if I enlarge this, if I enlarge this part of the string, so here's the string, and then I have marked two things like this, right? So here this is T and this is T. So this is the tension. Now this is the tension force acting on the mass. Tension force, tension acting on the mass. For certain things, it feels like repeating for Hirosh, but since they are joined today, so I have to repeat certain things here. So I hope you are okay with that. Okay, so tension acting on the string by the mass. And this is the tension. Sorry, here I have the tension acting on the mass by the string. The tension acting on the mass by the string. And here, if you consider this one, this is the tension acting on the string by the mass. So tension acting on the string by the mass. So if you consider this as the action and this is the reaction, Newton's third law. Every action has equal and opposite reaction. Equal in magnitude, opposite in reaction, force. Every force has equal in magnitude, opposite in reaction, force. Okay. So now if we consider this mass, capital M, simple M. So if I consider only that mass, what are the forces acting on it? Mg vertically downward, and then tension will be there. It experiences a tension from the string. So that is T. So if you consider the vertical equilibrium, T must equals to mg. T equals mg, right? Suppose let's say the mass is 4 kilogram. So then if you multiply with 10 ms minus 2, so 4 kilogram into 10 ms minus 2, you get 40 kg ms minus 2, which is Newton, 40 Newton. So therefore, if the mass is 4 kilogram, the weight will be 40 Newton. Therefore, tension in the string also 40 Newton, right? So now, since this string is light, that means it has no considerable weight. So the tension everywhere will be same. Here also T, every point will be the same tension. Here also the tension will be same. So always remember, if a string is light, then the tension everywhere will be same if it's hanging vertically. Okay. If you have any questions regarding this, you can ask. Is my voice is lagging? I got a message from a student, my voice is lagging. Let me confirm with Hirosh because I want to make sure whether it's my connection or a student's connection. Hirosh, is my voice is okay? Is it lagging? Okay, I got a message from Fabi, not lagging. Okay. So I think it's not an issue from my end. Okay. Okay, do you have any questions regarding this part? Okay, so here, those who are the new students here from the new batch, now here I have marked only the forces acting on the mass, right? I didn't mark any force acting on the string. So this is, we call the free body diagram. We call this free body diagram. Free body diagram. That means you mark the forces acting on it. Now, if I ask you to draw the free body diagram of the mass, then we have to mark only the forces acting on that mass. So if I ask you to draw the free body diagram of the string, then you have to draw only the forces acting on the string. Okay. So it will be clear now when we do a question. So let's start a question so that it will be like a example for you. The first question. Okay. If you are done writing with this, so I can move on to the question. So here the important thing I wanted to understand is in this case that if the string is light, then tension everywhere will be the same. And now if you consider the equilibrium of this mass, P equals to mg, right? And here just I wanted to enlarge and show you this part. So it is not necessary to write down this. Okay. Okay, write down this question. Write down mass of a uniform string of length 2 meter is 4 kilogram. Is 4 kilograms. Full stop. A 8 kilogram mass, a 8 kilogram mass is attached at the bottom end of the string and a 8 kilogram mass is attached at the bottom end of the string and the string is accelerated vertically upward by applying a force of by applying a force of 240 Newton. So I'll draw the system. So here's the string. And a mass is attached at the bottom of the string. And the system is accelerated vertically upward by applying a force of 240 Newton. Okay. So the system is accelerated vertically upward. A, let's say acceleration is A, right? And the mass of this is 8 kilogram, right? And the mass of the string is 4 kilogram. So we can mark the forces on this box and the string. So we know the box has a mass, so it has weight vertically downward, let's say, so 80 Newton. Because mass is 8 kilogram, so weight we find weight equals mass into gravitational acceleration in g. So W equals, if mass is 8 kilogram, then you multiply with g is gravitational acceleration 10 meter per second squared. So we take 10 meter per second squared. So 8 into 10 is 80 kg ms minus 1. By the definition of Newton, kg ms minus 2 is 1 Newton. So we can write 8. Okay. So here the weight is vertically downward 80 Newton, and the string also have a mass 4 kilograms. So its weight acts from its center. So here the center point. So from here it acts vertically downward. So that is equals to 40 Newton. Mass is 4 kilogram. So it's 40 Newton. Okay. So draw this system. Let me know if you finish drawing and marking this. Okay, so you can write down the first question. So write down the first question. Draw the free body diagram of 8 kilogram mass and draw the free body diagram of 8 kilogram mass and string separately. Draw the free body diagram of the 8 kilogram mass and the string separately. So since this is the first question, I will help you out. So let's first consider the mass. So first I consider the 8 kilogram mass.
என்ன பண்டு இப்படியே போட்டீங்க டார்ச்சர் பண்றீங்க.
Okay. First I will mark the forces, free body diagram of 8 kilogram mass. So free body diagram means you have to mark all the forces acting on it, right? So here I'll take this. Okay. So what are the forces acting on this? We know its weight will be there vertically downward from the center of gravity. So weight downward 80 newtons. So this is 80 newton. And then if you consider here, the tension will be there, right? So here I mark the tension. Okay, so here I have to mark the tension acting on the mass. So it will be upward from this point. So this is the tension acting on this mass by the string. So we can mark that tension as capital T, or let's say we mark here T1, T1. So this is T1, right? Okay, so this is the free body diagram of the 8 kilogram mass, and then we can draw the free body diagram of string. Okay, for the string, so yeah, I'll draw the string here. So then what are the forces acting on it? So we can see clearly the 240 Newton force will be there. So it's vertically upward. Force is 240 Newton. And the string has a mass 4 kilogram, right? So there its weight acts vertically downward from its center of gravity. So the center of gravity will be at its center point, because we have considered a uniform string. So the question says uniform string of length 2L. So therefore its weight 40 Newton acts from its center point, so at the center. So since the total length is 2 meter, this length will be 1 meter. So from here to here, the distance will be 1 meter. Okay. Okay. So here we want to only free body diagram, so no need to mark this. Only the forces. Okay. So then the in down bottom we can see there is a tension. So this one is the tension acting on the string by the mass. So that is downward vertically. So that is T1. So this is the free body diagram, the string. Okay, please draw down this. Okay, anyone has any questions regarding this? Zufar, do you have any question? You mean the normal reaction force? Hirosh, do you mean the normal reaction force? Okay. So, okay, so now the normal reaction force is when two objects are in contact, right? So if the box is we kept in down, now let's say this is the ground, okay? And then if we keep the box on that, then there will be a normal reaction force. So this is the normal reaction force are acting on it. So an opposite reaction force acts on the ground, right? Now here what we do, we take this system by applying a 240 Newton force. The system is accelerating vertically upward, no? So that means the system is in the air, right? It is not in contact with the ground. Therefore, there is no normal reaction force. Is that clear? Because I am applying a force and accelerating vertically upward. So it's moving upward, right? So it's moving, accelerating upward. So there is no contact with the ground. So there is no normal reaction force. Hiroshi, is it clear? Here, when the system is accelerating, you can't write tension is equals to mg. So when the now in the previous case, the string is just hanging, right? So so mass is hanging by the string and it's in equilibrium. It's not moving. It's not accelerating. It is at rest. So if it's at rest or moving at constant velocity, we say that it's equilibrium. It's in equilibrium. That means forces are balanced. So when forces are balanced, then uh, tension is equals to mg. But now it is accelerating. So here we can't write the tension is equals to T1 equals to 80 Newton. If I write now, it's totally wrong, right? It is totally wrong because if I write like this, then the object has to be at rest or moving at constant velocity. But it is accelerating vertically upward, right? So therefore, the T1 must be greater than 80 Newton, right? If I want to accelerate, if I want to lift this up, So I have to apply a force that is greater than its weight. Otherwise, now let's say this is the ground, this is the object. Okay. So here is the ground. Let's say this ground, and object is placed on, for example, table. On a table, I have placed the object. So if I apply a force, it's not coming because I am applying a force that is smaller than the weight of this object. If I want to lift this, I want to apply a force which is greater than its weight, right? Now, if I, for example, if I ask a small kid to carry a gas cylinder, will that small kid able to lift? No, because that small boy cannot give a force greater than the weight of the cylinder. If we want to lift that up, he has to give at least the force equal to the weight of the cylinder. Then only it can lift. Okay, so here the tension must be greater than the weight. Okay, so these are the free body diagrams. Okay, and then I'll give you the second question. So write down the second question. Find the acceleration of the system. Find the acceleration of the system. Find the acceleration of the system. We need the free body diagrams. Need. So the next question is find the find the acceleration of the system. Okay. So let us mark the acceleration of the system is A. That means the string is also accelerating vertically up with A acceleration. A is the box is also accelerating with the same acceleration. Now, for example, you are inside a car. If the A car has 10 meters per second squared acceleration, then whatever the things and the people inside the car will also have the same acceleration. If the car is moving at 5 meters per second squared acceleration, so all the things inside the car and the uh, people inside the car, everything or every part of the car will have the same acceleration. If you consider the side mirror, that one also have the same acceleration as the car, right? So here the system is accelerating with a acceleration, therefore the string also have the same acceleration, and the mass also have the same acceleration. So here we had to consider the string is inelastic, right? So string is inelastic. Then only they will have the same acceleration. String is inelastic. Inelastic means the length does not change upon applying a force. So now if I apply a force, this one doesn't change the size. I'm pulling both sides, again it doesn't change its size. So therefore this is an inelastic object. But if I can take a rubber band, if I apply a force, it will extend, right? So it's a elastic, right? So here we have to consider or inextensible. We say that inextensible. There won't be any extension. Inextensible string. So that's the best word we can give here at the moment. So we write in the bracket string is inextensible. Extensible means can be extended. So inextensible means can't extend. Inextensible. INEXPENINSIBLE. Okay. Did anyone found the value of the acceleration? Just I'm asking. Okay, so here we want to find the acceleration, so therefore we can apply Newton's second law, F equals ma, right? So here we can write applying Newton's second law. So to the system, we had to say for what we are applying, to the 8 kilogram mass, or for the string, or the system. System is this entire thing. Okay. So here I am applying Newton's second law to the system. So we had to consider direction also, because force is a vector. So I am applying vertically upward. So F equals ma. So what are the forces acting on the system? So we can see this 240 Newton force will be there. So this 240 Newton force, right? So it's vertically upward. So it is 240. And here the weight of this mass will be there downward. So I'm applying the equation upward, but the 40 Newton is downward, opposite to the direction I'm considering. So it's minus 40. And here this one also have minus 80 downward. But if I consider the tension, so this tension is a internal force pairs. It is not an external force to the system. But if I consider this mass, so for this mass, tension is an external force, right? For this string, this tension is external force. But if we consider this entire system, it is not a external force. They are internal force pairs. Okay. So only the external force. Now here applying force 240, gravitation attraction acting on this string 40 Newton, gravitation attraction force acting on this 80 Newton. So only these are the external forces, but the tension is an internal force to the system, right? But if you consider separately, if you consider only the box, then the tension will be an external force, and the weight of that box is a this mass. Weight of this mass is a external force, right? Similarly, if you consider this string, then this 240 is external force, its weight is external force, because it's gravitation attraction force, it's attracted by gravity. So gravity, and then the tension, this tension is the mass is pulling that string, right? Okay. So these are the forces acting on this system. So we have marked all the forces and the mass. So I'm applying the Newton's second law for the system. So you had to write the mass of the system. So the mass of the system is 4 kilogram plus 8 kilogram. So 4 plus 8. That is mass of the string and the mass of the object, plus the system is accelerating vertically upward with a acceleration. So 240 minus 40 is 200, 200 minus 80 is 120, equals 4 plus 8 is 12 into A. Therefore, A equals to 120 divided by 12 is 10 meter per second squared. So this is the acceleration of the system. Okay, please let me know in the chat box whether you understood or not. You can, if you understood, you can say yes. If not, say no. Please, I need a response from each and everyone. Please drop a message to the Knowledge Institute. I got 2 yeses, 3, okay, 4. How many are there in total? 5. 1, 2, 3, 4. 6. So yeah, 6 are there and 2 are absent today. Okay, so here 40 Newton is the weight, right? The mass of this is 4 kilogram, no? So therefore weight is 40 Newton. So weight we calculate as mass times gravitation acceleration. So if you know the mass 4 kilogram, you can simply multiply by g, which is 10, then it will be 40. Suppose let's say mass of object is 24, then the weight is 240 Newton. You have to simply multiply by 10 to get the weight, right? So the mass of the string is 4 kilogram, therefore its weight is 40 Newton. And we know weight is always acts vertically downward. If I drop this, it falls downward always because the weight is acting downward. The gravitation attraction is always towards the center of the earth, right? So likewise, now this one has 8 kilograms, so its weight is vertically downward 8 Newton. Right, so here I'm applying Newton's law, F equals ma, Newton's second law, vertically upward. So I'm considering the direction, positive direction as vertically upward. So in upward, only the 240 Newton is there, but the weights are downward, it's acting downward, so therefore it is minus. Okay, so therefore it will be minus here. So then we can find the total force, so which is net force 240 minus 40 minus 80, it will be 120. So 120 equals 12 times a, therefore a equals to 120 divided by 12, which is 10 meter per second square. Okay, so now I'm asking another small question, third question. So it's easy one. Which third question, what is the acceleration? What is the acceleration of the 8 kilogram mass? Okay, let me know the answers in the chat box. What is the acceleration of the 8 kilogram mass? වැරදුනාට කමක් නැහැ, තමන්ට හිතන දේ මේ chat box එකේ දාන්න please. I need a response from each and everyone. If you don't know means at least you can say don't know. Okay, I got one answer. It's correct. I got the answer from Hirosh. It's okay if you got wrong. You are learning. This is not an exam. Okay. I got 3 answers. 2 of them are correct. What about the others, please? Atika, Abhi, and Farwin. Okay, so here the acceleration of 8 kilogram mass will be the same as the system, right? So the system is accelerating with a acceleration, therefore the same acceleration. Very good, Abhi. Okay, so This one also have the same value, 10 meters per second square, and the string also have the same value, because entire system is accelerating, right? We have found the acceleration of the system, right? Now let's say you are inside a car. The car is accelerating with 5 meters per second square. So you also have the same acceleration relative to the ground, right? So if you consider the seats inside the car, that one also have the same acceleration, right? Okay, if you consider the what else, maybe silencer of the car, that one also have the same acceleration as the car, right? So now the string and the mass both are attached rigidly in the same system, so they also have the same acceleration as 10 meters per second squared. Okay. Okay, and then fourth question. Write down question number 4. What is the tension at the bottom end of the string? At the bottom end of the string. What is the tension at the bottom end of the string? Okay, try to find that. I'll give you a minute to play with this physics question, and then I will explain. Sorry, actually 3 students are absent today. If anyone got the answer, means you can share it with me so I can check whether you are correct. And it's totally okay to be wrong. I would appreciate you are sending the wrong answer than uh, staying silent. Okay, I think I got an answer. 50 Newton. Okay, we'll check. Okay. What about, okay, and 40 Newton, 80 Newton, 80 Newton. Okay. So here, now we want to find the tension of the string. So if I consider the system, then I won't be able to find, because the tension is the internal force pair to the system. So therefore, we had to consider either this mass or the string, right? So we can consider either the mass or the string. Okay. So you can consider either, and either you want if you want you can consider the mass, or if you want you can consider string. So anyway, since we are learning process, I will do this problem considering the both mass and the string. So first you consider the mass, so which is easy, right? So we know that this mass also accelerating with same acceleration a, 10 meters per second square. So here we cannot consider the force balance, right? in the previously, if we have just the mass is hanging there, then the tension equals to mg, but the mass is accelerating, so the tension is not equal to its weight. So here what we had to do is we had to apply F equals ma. So we can write using F equals ma, so vertically upward to the mass. You have to state to which you are applying. Okay, so I'm applying to the mass. So if I consider, so this is the free body diagram of the mass. So vertically upward we have T1 and downward 80 Newton equals to the mass is mass of this is 8 kilogram, right? 8 kilograms. So 8 into acceleration we found that is 10. So this acceleration 10 meters per second square. So 10. So therefore T1 minus 80 equals to 80. So therefore T1 is equals to 80. The minus 80 comes to the other side as plus 80. Therefore T1 is equals to 160 Newton. So the tension of the string is 160 Newton. Now that is obvious. Now you have a string, let's say you have a string and the mass is attached. So if the mass is just hanging by that, the tension in the string is equals to the mass. But if I'm pushing and accelerating, so then the tension will be higher than the mass, higher than the weight, right? So here the weight is 80. So but if you're accelerating, pulling that by the string, then definitely the tension will be greater than the weight of that mass. So therefore now you can see here it is 106 Newton. Okay, let me know genuinely if you understand this getting 160 Newton. If you understood, you can say yes. If not, say no. Okay, okay, I'll explain it again. Right. So here I am applying Newton's second law, F equals ma to the mass. So here's the mass. My mass second. Right. So if I consider this mass, we are considering vertically upward direction. So we had to consider the vertical forces. So the vertical force we have is T1 and 80 Newton. So T1 is upward and 80 Newton is minus. We are considering vertically upward direction, but this is downward. So you can indicate the direction here, right? So then this will be the resultant force. T1 minus 80, the net force is equals to mass is 8 kilogram times acceleration. F equals ma. We are just writing F equals ma. So F is the net force. So this is the net force. So I am pushing this side. I am applying a force vertically upward, but the gravity is pulling downward. For example, let's say there is a box here, on a ground, and you are pushing this by 50 Newton, but your brother is pushing this the opposite direction 20 Newton. Then therefore overall this direction 30 Newton will be there. Similarly, the tension will be there upward, but gravity is pulling downward with a force of 80 Newton. Therefore, resultant is T1 minus 80 Newton. Right? So, therefore, that is the resultant force. T1 minus 80. So that is equals to mass times the acceleration, where acceleration we found already, which is 10 meter per second square. That is the acceleration of the system. That means everything will move with the same acceleration. The mass is moving vertically upward with the 10 meters per second square, and the string also have the same acceleration. So here, so therefore acceleration is 10 meter per second square. So therefore T1 minus 80 is equals to 80. So minus 80 goes to other side. So it's plus 80. So therefore tension is equals to 160 Newton. Okay, good. So therefore that is the tension in the string. Now I told you I will do this question by considering the 80 kilogram mass and also the string. So now I do this considering the string. So we had write applying Newton's second law F equals ma to the string. So I am applying to the string. Here again I consider vertically upward direction. So in vertical upward we have this 240 Newton, and then downward minus 40 is there, and then downward the tension by the box is pushing the string downward, minus T1. So this equals to the mass of this is 4 kilogram, the mass of the string is 4 kilogram. 4 into acceleration is we know it is has the same acceleration as the system. So 10 meters per second square. So 10. So let us now try to simplify this. So 240 minus 40 is 200. I take this minus T1 term to the other side. And here this plus 40, 4 into 10 is plus 40. I take that term to this side. So here minus 40 equals to T1. So therefore, you can see T1 is equals to 200 minus 40 is 160 Newton. So by applying to either for the mass or for the string, you can find the tension. So you get the same value, where tension is equals to 160 Newton. Is that clear, everyone? Okay, please write down the answer for the question number 4. You had to write both the methods. That means applying for the mass and also applying for the string. When you are doing questions, then you have to do apply only for one, but now we are in the process of learning, studying. Okay, so here you have to write both the methods. And very importantly, when you are attending to the online class, you should not do any other work, like maybe going for a day out or like a relative place and staying there and studying. Don't do like that. Okay, when you're attending to the class, it has to be like yeah, like you are staying in the physical class, right? You had to be with your notes, books, and in your study area. Now if you have a study room, you had to be there, and you had to give the 100% attention to the class. Okay, no, don't do any extra work. Okay, only one thing that I allow is if you feel hungry, you can have your dinner while studying. The best thing is better you eat your dinner before class starts. Okay, so that's the best thing I prefer. But if in case if you got late, if you forget, and if you feel hungry, still it is permissible to have your meal while studying. But uh, when you have to use a spoon, because you have to write the notes and all, right? So please give the 100% attention to the class. This is very important. It's just not you attending 3 hours and sitting and taking the notes. It's about your future. It's about your life, right? If you study well, you will perform well in your exam, so that you will reach to higher status in the society. Okay, so this is very important. Please consider this. Okay. දැන් මම මේක කියනකොට සමහර අය ගෙදර ඇඳේ හාන්සි වෙලා මේම ෆෝන් එක තියාගෙන ඉන්නවත් දන්නේ නැහැ. Who knows? So please don't study like that. You have to sit properly, arrange your study area, take your notebooks, notes. You should have 2 books, when you are in the online class. So one is for the theory and three books actually, and the other one for questions. Like if I give past paper questions, like sometimes when I'm doing a lesson, I give a question from previous lesson. Like let's say for example, equation of motion. So those things and all additional questions and all you have to write maintain a question book as I have already discussed. Okay, by the way, I didn't discuss this with the new batch students, but the previous batch students, I have told these things, right? And also you should have a small pocket short notebook, right? So if there's anything short note, you can note down there so you can carry on that book with you, right? So these things are very crucial, okay, very important. Okay, okay, and please write down both the methods. Okay, okay, somehow I will discuss about it. So today the attendance we have is Fareen, Atika, Abi, Samha, Hirosh, and Zufar. Six are there and three are not attended today. One is Rashid, and Ikram and Minna. Three students hasn't joined today. Anyway, so having issue attending for the class on Tuesday. They're having some, I think, biology class, I guess, on Tuesdays. Is it possible for us to change the class day? So let's go for a voting. Uh, how about Monday? Monday, okay, Monday also I think not possible, I guess. Then Tuesday, so it's today. Wednesday, at the moment, I'm doing 2025 batch class. I want to check whether they are able to shift. Then Thursday, is quite difficult for me. Okay, let me check. Right. Tuesday, Wednesday. Okay, let's vote for the Wednesday. So yeah, Tuesdays there are two students having an issue with Tuesdays. So let me check. Okay, so Wednesday class, I think only Thursday. Okay, then Thursday, how about I have an individual class? I think I able to shift that. Then let's do a voting on Thursday. Let me know uh, whether you all can attend on Thursday. I need a response from each and everyone. It means six are there, so I want a response from each six students. Okay, so 2 yeses for Thursday. The four more. Time, the same time it will be like 8 to 11. Okay, Hirosh has class 6 to 9. Atika have biology class on that day. Atika, what about you on Tuesday? Do you find difficulty on Tuesday? As I spoken to your mom, she said that you have class on Tuesday. Only for today it's possible, is it? So do you have classes on Tuesday? Atika? So you have class on Tuesday, no? Okay, then it seems most of you have class till 9. Or else what we can do is now, for example, today 8 to 11 means 9, 10, 11. We can do only 3 hours now. Or maybe if I continue up to 11:30, 3.5 hours, right? So by that time, most of you will feel sleepy also. So what we can do is we can uh, divide the class into 2 days, like 2 hour sessions. So for example, if I say Monday 9 to 11, and then another day Thursday 9 to 11. So that way, I think most of you can join, right? So what do you think about it? So that way we can do more hours also. Monday until what time you have class, Zufar? 9 to 11. Oh my God, same time. Okay, so Monday you have class till 9:30. So Monday is not possible. Tuesday, if I started at 9, somehow will you be able to join it? At what time, until what time you have classes on Tuesday? Samha and Atika, can you text me your Tuesday class time? Samha and Atika, please. How about Atika? So Samha can join at 9. Okay, Atika can join at 9. So I think only Samha having an issue. So Atika also have class until 7:15. So Atika, you can join at 8 o'clock, right? In the usual, I mean, regularly. Can you join at 8 regularly? If you find difficulty in texting, because texting is slow, so that you can uh, unmute and talk. You can speak. Atika, are you okay to join at 8? Would appreciate if you respond soon, so we can start the class. Around what time you will be joining? Sorry, around what time you will be reaching the home? 8:20. Okay. Okay. So then we will do like this. So Tuesday 9 to 11, everyone can join. Okay. So Tuesday 9 to 11, and then so Monday is not possible. Tuesday, Wednesday, Thursday 9 to 11. Let me know Thursday 9 to 11 who can join. Okay. I got 2 yes, 3 yes, 4 yeses, another 2 yes. Okay. And how about Farwin? I think you're okay, right? To join on Thursday 9 to 11. Hmm. You have a unique class. Okay. How about? I think that's the best option we have. Yeah. Is it okay if until what time you have unique class on Thursday? Seven to 10. So I think only 1 hour will be a clash for you. Is it okay to send? I mean, go through the recording for that missing 1 hour. Okay, thank you. So we'll schedule the class like this. So Tuesday 9 to 11 and Thursday 9 to 11. Okay, so this way we can do more hours. So we can see it's 4 hours, right? Yeah. So I'll reconfirm this by dropping a message in the group, right? So it's almost confirmed actually, but I will, what you say, Sahateekarana certificate at denna by dropping a message in the group. Okay. Okay then. So let's come to the session, and thanks Amma reminding about the timetable. Okay. Okay, I hope you all wrote this. Okay, then I can move on to question number 5. So question number 5, write down. Uh, okay, by the way, I just remembered Thursday I have one class I'll reschedule it. It's fine. Okay, so we have confirmed the timetable is confirmed. Tuesday and Thursday 9 to 11. Okay. So the question number 5, what is the tension? What is the tension at the middle of the string? At the middle of the string. Okay. ඒක හොඳයි අපි දවස් දෙකකට දාගත්තේ නැත්නම් පැය තුනක් එක තැනක වාඩි වෙලා ඉන්නවා කියන එක උගන්ගේ හැටියට අමාරු දෙයක්. So it's better we divide the class, segregate the class into 2 days as 2 hour, 2 hour. And that way we can do more hours also. And by the way, there is no change in the new batch timetable. That will be as usual Sunday morning. So the new batch, there are 2 times available. One is Sunday morning, 8:30 to 12. But I have to change the timetable. I mean, we want to make it for starting from 7:30 so that we can finish at 11, because After this class, I have to travel to Dehiwala to start the other class. So that will be 1:30 to 5. Okay, what is the tension at the middle of the string? So the midpoint you can find here. So here's the point, the midpoint. So at this point you want to find the tension, right? Okay. So since this is the first question, I will explain this. Okay, I already got an answer as 40 Newton. Let us see. Appreciate. Okay, so for this, what we can do is now here, if I consider the entire string, I won't be able to find the tension. If I consider the entire string, I won't be able to find this tension. So therefore, what I have to do is I have to consider either uh, top half of the string or the bottom half of the string. So I have to consider either the top half of the string or the bottom half. Either I had to consider this part or the other part. So I had to consider either this part of the string or this part of the string. So this question also I will do by considering the both parts. I mean, first I will do with this, and then second I will do with this, right? But if in a question, just only considering one part is enough. So here, so I mark the tension at the middle of the string as T2. So I mark this tension as T2. Okay. So here, this one I have marked is the tension acting on the top half of the string by the bottom half of the string. And this one I have marked, this is the tension acting on the bottom half of the string by the top half of the string. Okay. So now I consider first the top half of the string, this part of the string. Okay, so here again I have to draw the free body diagram to explain you so that it will be very clear when we are applying the F equals mv to find the tension. Okay, so if I consider this, what are the force acting vertically upward? 240 Newton will be there. 240 Newton. And here at this point, the T2 acting downward. So that is the tension acting on the top half of the string by the bottom half of the string. From this point, I mean from this point, from this point down, this string is there. That string will push the top string, right? So the tension there is T2. And now this one has mass, and also the string is uniform. So if the total length in 2 meter is 4 kilogram, so 4 kilogram is the mass in 2 meter length. So here we have considered half of it. So 1 meter, the mass will be 2 kilograms. So its weight acts from the middle of this part. So vertically downward, 2 kilogram means 2 into G is 10, 20, 20 Newton. So these are the forces acting on this top half of the string. So this is the free body diagram of the top half of the string. So then I can apply vertically upward F equals ma, because we know this string is accelerating 10 meters per second square. Therefore, the top half of the string also have the same acceleration. So the forces we have 240 minus downward 20 minus downward T2 is equals to the mass of this is 2 kilogram, because total mass of the string is 4 kilograms. So half of the string, the mass will be half. So 2 kilogram. 2 into A is acceleration, we already got 10. Right, therefore 240 minus 20 is 220 minus T2 equals to 2 into 10 is 20. So I can shuffle, that means I can take this minus T2 to the other side, 22 to this side. Okay, so then we have 220 minus 20 equals to T2. So therefore T2 is equals to 200 Newton. Right? So T2 is equals to 200 Newton. Okay. So this one I obtained by applying F equals ma to top half of the string. Right? So then now I'll find using F equals ma to bottom half of the string. Okay. So then again, first thing what we had to do, we had to draw the free body diagram. We had to draw the free body diagram for this part. Okay. So let me draw the string, bottom half of the string. So it is here. This space might not be enough. Okay. So now we'll mark the forces acting on it. So now I'm drawing this part. Okay. So what are the forces vertically upward? We have T2. So this is the tension acting on bottom part of the string by the top part of the string. And then here the tension T1, which is we already found that as T1 we found earlier, right? We got 160 Newton. So 160 Newton. So this is the tension acting on the string by the 8 kilogram mass. The tension acting on the string by the 8 kilogram mass is T1. And this one also have a mass of 2 kilograms, so it is weight vertically downward 20 Newton. So therefore we can apply F equals ma vertically upward to this part of the string. F equals ma. So T2 minus downward 20 minus downward we have 160 is equals to the mass is 2 kilogram into acceleration is 8. So T2 equals to acceleration we take 10 because we found that 10 meters per second square. 10. So here 20. So minus 20 comes to this side as plus 20 minus 60 comes to this side as 100 plus 160. So T2 is equals to, again we get the same value as 200 Newton. Right? So again see we get the same answer here, 200 Newton and 200 Newton. So you can consider, if you want to find the tension here, you can consider either the top half of the string or the bottom half of the string. Okay. Do you have any questions? If you have any doubts, you can clear it now. Okay, I think everything is fine, right? Okay. Okay, so please write it down. Here also you have to write both the methods, right? Considering to the top part of the string, it's the method 1, or applying if equals ma to the bottom part of the string, that method 2. So you have to write both methods because you are learning. Okay. And by the way, we have scheduled the class on Tuesday and Thursday, but this Thursday you won't be having the class because I already have a class. So this week I will inform to those students and I'll change the class timetable. So this 2 hour will be applied from next week. Okay. So this week again, then no classes there. I mean, the from mechanics part. I mean, okay, for those students who have new batch students, you have your regular class on Sunday. Okay. Okay, let me know if you finish writing this in the chat box. Okay. If you are still writing, you can take a screenshot and then you can complete it later. Right. Okay, so the next question, the main question. Two masses, two masses, 5 kilogram and 4 kilogram is attached at the ends of a of an inextensible uniform string of mass 1 kilogram and length, mass 1 kilogram and length, length will take. I think length is not necessary for this position. Yeah. So mass 1 kilogram, no need to length. The 5 kilogram mass is at the top end of the string and the system is accelerated, vertically upward by applying a force of 200 Newton to 5 kilogram mass. Two masses 5 kilogram and 4 kilogram are attached. So here it's a plural, so it has to be are attached at the ends of an inextensible uniform string of mass 1 kilogram. The 5 kilogram is at the top end of the string and the system is accelerated vertically upward by applying a force of 200 Newton to 5 kilogram mass. Okay, so first I will draw the figure. Okay, so this is 5 kilogram mass and this is 4 kilogram and the mass of the string is 1 kilogram. Its system is accelerated vertically upward by applying a force of 200 Newton to 5 kilogram mass. The system is accelerated vertically upward. Say acceleration is marked as A. Okay, so let's mark the other forces acting on this. The external forces are the weight vertically downward, here 50 Newton. Newton, and the weight of this vertically downward 40 Newton, and there is a tension here. So this is the tension acting on the box mass. The tension acting on the mass by the string, and this is the tension acting on the string by mass. So let's take T1. So that's the action reactions, Newton's third law. So magnitudes are same, T1, T1. So here we'll mark the tensions here. So this is the tension acting on the mass by the string, and this is the tension acting on the string by the mass. Let's mark that T2, T2. Okay, so the first question is, draw the free body diagrams of 4 kilogram, 5 kilogram and string separately. Okay, so please draw quickly and send your show me your answers. You can send it in the chat box. You can write the answers, and once you're done, you can capture it and send. Okay. Once you're done, you can capture your workings and send it to the Knowledge Institute, not to Rimaz. Okay. You have to send it to the co-host. Okay, Hirosh, you can send it then through WhatsApp. If you find difficulty in any problem sending to the Knowledge Institute in Zoom chat, then you can send it through the WhatsApp. Okay. Okay, so this is the answer of one of the students. So let's examine this. Okay, so 5 kilogram. So if you consider the 5 kilogram mass, so we have the 200 Newton force vertically upward, right? That is correct. The 200 Newton force will be there. That's correct. So this is correct. And here, when you're marking this 50 Newton, which is I think the weight of that. Okay, so here it should you should draw like this from here. You have to mark it here because now here you can see it's the tension also there, so you don't overlap the tension acting from this point, right? So therefore we had to mark like this. So 50 kilogram Newton you mark here, right? So you mark 50 Newton, and then from this point downward, T2. We usually mark the tension with capital T, so you can mark T2 there. Okay, so that's correct. Only thing is that small difference you have to make. Okay, and then if you consider the 4 kilogram mass, so its weight vertically downward 40 Newton, correct, and then the tension T1 here. So I have taken here capital T1, so I will go with the capitals here, and usually we take capital for the tension T1. That's correct. Okay, the tension, then the string. So when it comes to string, by the way, here the thickness of the string is much. So reduce the thickness here. This is the thickness is so it's more. The thickness is more, so we have reduced the thickness. And so if you consider that this one here, we have T2 at the top end, correct, and at the bottom end T1 is there. Correct. Now you can see that tension in the string. So at the top end and the bottom end, you can see the tension acting in outwards, so that there is a tension force, tensile force, right? The string is under a tension. So because in the both ends you can see the forces, the tension force acting outwards of the string at the end points. So it is actually originally experiencing a tension force. And then its weight will be the downwards 10 Newton. So that's very good. Okay, good. Okay, so this another spoon is working. So appreciate for sending the answers. So then we can see, we can discuss this, right? So here, that force, now this is for 5 kilogram, 4 kilogram, or 5 kilogram. Wait, check. Five. Yeah. No. So, okay, so I'll explain this again. The free body diagram. There's much to do. Okay. And any other answers I have got? Yeah, you have to separately consider the, because it says 4 kilogram, 5 kilogram string separately. Okay. Any other answers I have got? Miss Farwin, please, if there's anything, please drop a message to the Knowledge Institute. Can you send it to the Knowledge Institute, because I'm unable to share it. I think your answers are correct. Yeah. Okay, so here I will start with 5 kilogram. So first 5 kilogram mass. So for this, now I had to consider only, I had to draw only the 5 kilogram mass. Okay, because I'm drawing the free body diagram of 5 kilograms. Right? So by the way, this one, this here, this is actually the free body diagram of the system. This is the free body diagram of the system. I have marked all the forces in the system. So this is the free body diagram of the system. Okay. Now here we want to mark the free body diagram of the 5 kilogram. Then you have to mark only the 5 kilogram, draw only the 5 kilogram mass and mark only the forces acting on it. So the forces acting on it are vertically upward 200 Newton, and its weight vertically downward 50 Newton, and then the tension acting on it by the string, that is T2. So these are the forces acting on 5 kilogram mass. And then we can draw the free body diagram of 4 kilogram mass. So then we have to draw only the 4 kilogram mass there. So then what are the forces acting on it? Its weight vertically downward 40 Newton, and the tension by the string T2, right? If this string is not attached to this mass, the mass cannot accelerate. We are applying the force here. So this force will accelerate this 5 kilogram. Since this 5 kilogram is attached to the string, it pulls the string vertically upward with the same acceleration. And since this string is attached to 4 kilogram mass, it pulls the 4 kilogram mass vertically upward. So these are the forces acting on 4 kilogram mass, and then we have to mark the forces acting on the string. So let's mark the forces. So here at this point, the T2 is there. At the bottom, T1 is there. Its weight vertically downward. What is the mass? 1 kilogram, so 10 Newton. So these are the free body diagrams of each of the mass. Okay, if you have any trouble or any questions regarding free body diagrams, you can ask now. It is simple. If I say draw the free body diagram of 5 kilogram mass, so you have to mark only the forces acting on 5 kilogram mass. That's all. Okay. Quickly draw and mark this free body diagram, and if you're done, let me know. Say done in the chat box, so I can give the next question. Okay, Hiroshi is done. Okay, so I'll give the second question. Write down. If you're still writing, you can take a screenshot, guys. So the second question is, find the common acceleration. Find the common acceleration of the system. Find the common acceleration of the system. Okay. So find the acceleration. You have to find the value of A. Please, once you're done, show me the workings. You can send it through the WhatsApp or through the Zoom chat. I recommend you to send the Zoom chat to the Knowledge Institute. If you can't send to that, then you can send it to the WhatsApp. Okay. Okay, I'll check. Okay, so applying F equals ma to the system. So the forces acting on it are, so 200 Newton vertically upward, and then weight of this downward minus 50, weight of the string downwards minus 10, and then weight of this downward minus 40. And the total masses are 5 plus 1 plus 4. Okay. Good. So this is the net force. So 200 Newton is the only applied force to the drive force, we can say. So this is what carries every mass. And then this is the weights of each of the object. 5 kilogram mass, string, and the 4 kilogram mass, right? So therefore, now if you add these minus 50, minus 10, minus 60, and then minus 40, minus 100. So total weight is 100 newtons. So if you want to lift this, you have to apply a force of force greater than 100 newtons. Now this is 200 newtons, so that is greater than 100 newtons. So it's enough, that force is enough to accelerate this. Okay. So therefore, then the resultant force will be 100 Newton, and then total mass times acceleration. The F equals ma, the resultant force equals unbalanced force is equals to mass times acceleration. So the resultant force is 100, and then mass is here 10. So 10 you take to the other side, it becomes division. Okay? So here we get 100 is equals to mass is 10 times A. Therefore, A equals 100 divided by 10. Right? So therefore, A equals 10 meters per second squared. Okay. Did you all understand? I got another answer. Let me see. Yes, correct. F equals ma. So here you have to put mass times total mass times acceleration A. Right? Total mass times acceleration. So here 10 into A, right? 100 equals 10 into A. So therefore A equals 100 divided by 10. Okay. So therefore acceleration is 10 meters per second squared. So we can apply F equals ma to the system. So resultant force 200 minus 50 minus 40 minus 10 equals total mass 5 plus 1 plus 4 into acceleration. Therefore, acceleration is 100 divided by 10. So A equals 10 meters per second squared. Okay. So the next question, question number 3. Find the tension. Find the tension at the bottom end of the string. At the bottom end of the string. Find the tension at the bottom end of the string. Okay, so you have to find the value of here T1. Okay. Okay, I'll give you a couple of minutes to try this question. Okay, I got an answer from one student. What about the others? What is the value of T1? What is the magnitude of T1? By the way, here I had done a mistake. So here when in the 4 kilogram mass, it is T1 here, right? This is T1 because here it's T1. Okay. So okay, I got 3 answers and 3 of them are saying 80 Newton. Let's check whether they are correct. I hope all correct. Let's see. So to find that, what we can do is we can apply F equals ma, right? Can apply F equals ma to the 4 kilogram. You had to write this, huh? This is most important. You had to write. Otherwise, you may lose marks in your exam. If it's essay paper, you must write this. Okay. Applying F equals ma to 4 kilogram. So we can apply vertical upward. So T1 is there minus 40 equals to the mass is 4 times acceleration is 10. So therefore T1 equals 40 plus 40. Okay, good. Therefore T1 is 80 Newton. So therefore the tension at the bottom end of the string is 80 Newton. Okay. So the question number 4. Yes, you are guessed correct. The question number 4 is find the tension at the top end of the string. Find question number 4. Find the tension at the top end of the string. Find the tension at the top end of the string. Okay, so I got 2 answers, but they are different. So either one of you might be correct. Might be sometimes, maybe both of you can be wrong. Who knows? Let's see. But if both of you have same answer means, then might be both of you are correct. Okay, I'm waiting for the answer from others. Okay, I got an answer from Abhi, and that's tally with another answer, both are 100 newtons. Okay, let's see. Okay, so to find T2, we can consider either the string or the you can consider the string or the 5 kilogram. You can consider 5 kilogram or string, because if you consider the 5 kilogram here, this is known, acceleration known, only T2 we need to find. Or if you consider string, T1 we found and this is known, so T2 can be found, right? So you can consider either 5 kilogram mass or the string. So I will consider 5 kilogram. So using F equals ma to 5 kilogram. So vertically upward, what other force are there? 200. So the weight is downward minus 50, and minus T2 equals mass 5 into acceleration 10. So 200 minus 50 is 150, minus T2 equals 50. So take this T to the other side, 50 to this side. So it will be 150 minus 50 equals T2. Therefore, T2 is equals to 100 Newton. So the T2 is 100 Newton. So I got an answer from student. Let's see. Yeah, this from Abhi. So if equals ma to 5 kilogram, so 200 minus 50 minus T2 equals 5 times A. Therefore, T2 equals 100 Newton. Okay, good. So I got 100 Newton, but the method is different. Can you send your workings so I can check? If equals ma to 5 kilogram, so you're wrong now. Because when you consider the 5 kilogram, right? So it has, you can see here 5 kilogram. It has this 200 Newton and its weight 50 and tension downward T2. So two things are there, right? So the force vertical upward 200. So 200 minus the weight 50 minus T2 is equals to the mass times acceleration. Yeah. Okay. Okay, and the fifth question. Write down the fifth question. Find the tension at the middle of the string. Find the tension at the middle of the string. So at the middle you can consider as its T3. Okay, I got an answer. I'll be waiting for the answer from other students as well. Okay, I got one answer 90, another answer 95, and two answers 90. Okay, so I'll try. So you can consider either top half or bottom half of the string. Okay, so I'll consider the either one of that. You can consider either top half or the bottom half. So I consider the top half of the string. Okay, so for that, using f equals ma to top half of the string. So vertically upward, T2 is there, and minus T3, and also its weight. This part of the string has a mass. It has a weight vertically downward. So weight is vertically downward. So total mass of the string is 1 kilogram. So therefore this is 0.5 kilogram. So if you multiply with 10, so 5. So therefore 5 Newton. So the weight will be 5 Newton. As mass is 0.5, so weight will be 5 Newton. Minus 5 equals to the mass times acceleration. Mass is 0.5 into A. A we found already, which is 10. Okay. So therefore T2 we found already 100 Newton. So 100 minus T3 minus 5 equals 5. So I can take this T3 to this side. So then 100 minus 5 minus 5 equals T3. Therefore T3 equals 90 Newton. Okay, so the problem that two students, one student got 95 is because I think they haven't considered the uh, weight of this, I think, probably. Okay. Okay, do you all understand how this T3 comes 90? Understand that? T3 minus 5 minus 80. I think Arvind's your answer is wrong, right? If no, you can't consider the full weight. You are considering only the top half, no. So consider only we are considering only this part of the mass. So you had to consider only that. Okay. Guys, can you hear me? Sorry, suddenly the Zoom is disconnected in my desktop, so all the drawings gone off. Okay, I guess you all understood the ask method, right? The question, right? How to get the answer? And you all can try by applying to the bottom half of the string and get the uh, tension value at the middle of the string, and I can check whether you have done correct, or if there's any mistake, I can inform you, like, okay, so you can do it later, and you can send it to me WhatsApp. Okay, guys, can you hear me clearly, or my voice is lagging? And what about the video? Can you know? Okay, and is the video is lagging? Okay, thank you. Right, so we are done with that question. So let's write the new question here. Okay, so it's 10:59, almost time is right then. Okay, so then we will wind up the class from here. Okay, so if you have any questions regarding today's session, you can ask. And especially there are a lot of students from new batch, so you might have some difficulties, but I try my best to explain from zero to the lesson. So anyway, if you find anything, like if you have any questions, you can ask me now regarding the today's session. Any doubt or anything? Okay, thank you for the feedback, Samha. How about Atika? How was the session for you? Can you understand everything? Did you understand everything? Okay, so if you have no questions regarding the today's session, so we are good to sign off. Okay, then study well, go through the notes and practice these questions once again. And yeah, good night. See you soon. God bless you. Fi aman Allah. Bye.